So anyhow, let's retrace this for a second. So again, look, if we actually reset ourselves to the beginning, on the very first day of class, I mentioned two ideas that are familiar to most humans, and yet we don't quite understand what they are, even though we use these words. And we talked about this idea of area, and then this idea of speed and velocity. And what we sort of suggested through some intuitive arguments is that one way we can attack these problems was through these ideas of limits. And so it turns out that there's this real useful limit. If we take a difference quotient of a function and take the limit of that in a certain way, that limit is extremely useful. And as we'll see, it can be used to define things such as velocity. And it can also be used in a much more general setting to describe rates of change. And so since it's useful, we give it a name. Okay, so we tell you there's this operation on functions that's useful. We call it differentiation. And we're going to show you all kinds of applications of it in soon enough time. But we can't give applications of the derivative yet until we know how to compute them. I mean, if I tell you the derivative is useful for all kinds of stuff, but you can't compute a derivative, then what's the use of even doing the applications? So anyhow, that's where we're at. So we know the definition's challenging to work with. And what we want to do is we want to come up with simpler ways of doing it, procedural ways that we can do by hand easy, ways that we can program software and computers to do. And so what we saw last week is that polynomials are very easy to compute their derivative. And that's good news. And what we do is we hope that there's other functions follow suit. And luckily they do. So before we sort of continue with this, does anybody have a question? So comments? Okay, so what makes differentiating polynomials sort of easy is what we had this general rule called the sum difference rule that says if you look at this polynomial, it has three terms, 1, 2, 3. And so because of our limit laws, if I wanted to take the limit of those three pieces, add it together, what I can do is the limit laws say I can do each piece separately and then add the limits together. And so what that allows us to do in terms of the derivative is it allows us to differentiate each piece and then combine them at the end. And so that's why this is such a short computation. I do each piece. So there's three terms, I differentiate each term, and then I combine them back together. And we might ask ourselves, well, if that works for addition and subtraction, does it work for the other arithmetic operations? So let's make sense of that. So what makes them easy is what we call the sum difference law, or sum difference rule. And basically that was saying that if we take two expressions and add them together or subtract them, we'll call one F and one G, then you can differentiate each piece separately and then add them or subtract them back together. So again, let me emphasize this. And you think about it in English, you could say the derivative of the sum or the difference is the sum difference of the derivatives, or each piece, if you will. Now, the only downside to what we're going to say is that it doesn't seem intuitive. This seems intuitive to us, I think, that if you take two guys and add them together, that somehow their derivative should be the sum of their, the total, or excuse me, let me say that another way. If I create a new function by adding two guys together, it makes sense to think that the derivative of the new guy should somehow be made up of the derivative of each piece. And that's exactly what this is saying. And it works out in a very simple way. And by the way, this is true. You can write all this out, limit as h goes to 0 and all that. It's true because of the limit laws. It's not hard to deduce this. Well, you can read it in the book if you want it. And so the question then becomes, if it works for addition and subtraction, does it work for, say, multiplication? So instead of adding or subtracting, what if I multiplied two functions? Or instead of multiplying, what if I took the ratio of two expressions? Is there some sort of quote unquote simple formula for these kinds of ideas? So, of course, there's going to be a formula, because we wouldn't tell you this if there wasn't one. But the thing I'd hope that you would try to do is try to understand where these things are going to come from. So using the definition, we can deduce what I will put in quotations as simple formulas. Now, why do I put simple in quotations? Because simple is a relative term. But what I mean by simple is that it has a very nice structure, and there's symmetry, and it's not difficult to memorize, and it's not difficult to use, provided you practice. So the first one is what's called the product rule. Because it tells us how to differentiate the product of something. So it turns out that you don't just take each piece and multiply it together. It's a little more tricky than that. It's actually the derivative of f times g plus leave f alone and multiply it times the derivative of g. And don't forget, you might, depending on where you're reading this, if you're getting information elsewhere, there's other notation for this kind of expression. Some people might write it, some might write it like this: f times g prime is f prime times g plus f times g prime. That's another way to write the same formula, depending on what kind of notation you want to use. Now, when I say at the top of this screen, I say using the definition, that's exactly what I mean. If you wrote out limit as h goes to 0 and did all the algebra and did some creative sort of manipulations, at the end of the day, when you took your limit, what you would see is this thing on the right, f prime times g plus f times g prime. Does anybody have a question? Comment? Is anybody alive? Or are you all just sleeping? Which is fine too. I don't blame you. Okay, good. I really wish we were in a classroom. I hate this Zoom and stuff. I don't even know what any of you look like. All right, now I look like a train wreck. This lighting, it looks like I'm like on a, what's happening here? Okay, so let us, and by the way, what I would encourage you do when you're practicing these things is use some sort of, I don't know, is the word mnemonic? I don't know. So the way I taught myself this years ago is I would think of this as being two functions, a first and a second, f and g. And in my head, I say derivative of the first times the second plus the first times the derivative of the second. So let's do an example of how we might use this. So suppose I want to compute the following derivative. Let's say 3x squared times the quantity square root of x plus 1 over x. So the way I would encourage you to think about this is think about it is like you have two things being multiplied together. I can call this guy my g. I'll call this guy my f. And so since I'm trying to learn this, I'm going to use this mnemonic that I talk about. And so I know that this is the derivative of the first function times, leave the second alone, plus leave the first guy alone, times the derivative of the second piece. So if we use our color coding annotations, this is f prime, this is obviously f, and then this is g, and then this is g prime. And so now, once we've done this, it just remains to compute the derivative. So I could write this as, well, this is 6x times the quantity square root x plus 1 over x. And then this is plus 3x squared. And then what's the derivative of this piece? Well, by the sum rule, this is 1 over 2 root x, because that's the derivative of square root of x. And then it's minus 1 over x squared, because that is how we differentiated 1 over x. And so that is the derivative. Yikes. Of course, you could simplify that if you wanted, but right now we're not going to. Does anybody have a question about this? Going once, going twice. Commons? All right, so again, how do you get good at this? You do it. Luckily, there's lots of help. I mean, pretty much most calculators now can compute derivatives for you, so you have that to check your work. You have the internet has web pages and apps that do all this stuff. That still doesn't mean you shouldn't teach yourself how to do it by hand and understand what the derivative means and stuff like that. Okay. So similar to the product rule, is what's called the quotient rule. So this tells us how we're going to differentiate the quotient of two functions, provided it exists, the derivative at least. Now this one's a little more complicated. You take the bottom function times the derivative of the top minus the top times the derivative of the bottom all over the bottom function squared. Now, again, there's very little intuition for why this formula is so wild looking. And in my opinion, if you're really concerned, you know, some of you don't care where it comes from. You just want to memorize it and you learn how to use it. And that's fine. I don't begrudge you for that. But I would highly encourage that you think about where this formula comes from. And what I mean by that is, can you derive it? Can you write out the limits and do all that arguments? Can you figure out how to derive or deduce this formula? It's challenging, but if you can deduce it, then it shows that you have a solid understanding and an idea of how this kind of stuff works. It's done in your book. It's not hard to find on the internet. I don't know that it's beneficial. It's not beneficial for me to do it for you because that doesn't do anything. You don't learn from watching me. You learn from doing these things on your own. Does anybody have a question about this before we do an example? Okay, so let's look at one. Hold on one second, guys. All right, sorry about that, guys. I need a bigger house. Anyhow, isn't this fun? So let's do an example of the quotient rule. So let's take something like 3x squared over 5x plus 7. So we want to know the derivative of this particular function. So how do we do it? Well, we know it's the bottom function times the derivative of the top minus the top times the derivative of the bottom. So one of the things you have to be very careful with the quotient rule is there's this minus sign. So if you get things backwards, it's going to be wrong. So you got to be mindful of which order you're doing it, and you also have to be mindful of your grouping symbols. So I'm going to be very careful with doing the next step. And one of the things that will happen, because this is always the case, some of you have done this before, or some of you are better at it than others. That's okay. It's a skill. Some of you are faster than others if you ran a race. Some of you are stronger than others. So it's natural for us to have differences in our abilities with everything. Some of you read faster than others, whatever. So some of you are going to get good at this quickly. You're going to be able to skip steps. That's fine. Some of you will struggle with this all semester, and that's fine too. There's no award for speed on this. And to be fair, it doesn't even matter if you're fast, because you're never as fast as a computer. So what you should do is concentrate on taking your time and understanding the logical steps that we take at each place in the problem. So the next step would be to evaluate these derivatives. So this is 6x. And then this guy is just 5. And then the bottom, I'm just going to leave squared. And I guess if I wanted, I could clean this up by doing some simple algebra. I'm left with 30x squared plus 42x minus 15x squared all over the bottom squared, which finally simplifies to 15x squared plus 42x. Like this. Now, what I would want you to ponder is, could you imagine if I said to you, I want you to compute this this derivative from the definition? So another important thing I really want you guys to sort of think about is that even though this looks like a messy calculation, it is nothing compared to how messy the calculation would be if I said you have to take the limit as h goes to 0 and use that definition. So even though this looks messy, it's far less tedious than using the actual definition. And if you don't believe me, go for it. Try to use the definition. Evaluate f evaluated at x plus h minus f of x over h, and take that limit. Your head will explode. Any comments, questions? I wonder if you guys would talk if I offered money. Or not even just money, currency of points. Like I would say, whoever talks the most in the Zoom class gets 1 letter grade tacked onto their exam. Would you talk then? Okay, so hopefully you guys will, we're going to do plenty of examples of this stuff because we're going to give you a bunch to do on your own. And so we'll continue to do examples. But I hope you take the time to understand what I mean when I say this is we're using shortcuts here. And these shortcuts are deduced from the definition. So I would highly encourage you to challenge yourself to see if you can to make sense of that. And here's a consequence of the quotient rule. So we can extend the power rule to negative exponents. So what do I mean by extend it to negative exponents? Well, so far the power rule were this nice thing. Here's the power rule. So we said you multiply by the exponent, and then you subtract 1 from the power. That's the power rule. But this was only true for n equal 1, 2, 3, 4, 5, 6, whatever, a positive integer. So this holds for any integer n. So we already know it's true if n is positive, but what if n is negative? So let's see. Let's prove it's why. Let's verify it. So in mathematics, we call this a proof. So oftentimes, if we're going to give a logical proof, we start it off by telling whoever the reader is, hey, we're going to prove this. And here's what we know. So we already know. I guess that. So we know it is true for positive integers. So instead of that, let's assume the integer is negative. So okay. So if I tell you an integer is negative, what can we say about it? So if n is negative, then n has to equal negative k, for example, where k is a positive integer. Right? So if I have negative 7, well, what is negative 7 equal to? It's equal to negative 1 times positive 7. That's what we're saying. We're saying any negative number can be written as minus 1 times a positive number, in particular integers. Okay, so what if I say that, what can I then deduce? Well, what's the derivative of x to the power n? Well, we can rewrite this using k, and this is the same thing as the derivative of 1 over x to the k. Which by the quotient rule is the bottom times the derivative of the top, which is just going to be 0, minus the top times the derivative of the bottom, all over the bottom squared. But when you compute this derivative, what you get upstairs is minus kx to the k minus 1 over x to the 2k, using properties of exponents. Now this looks ugly because we got lots of letters floating around, but when you first started algebra, you learned these exponent properties. You learned how to write, if I have x to a power upstairs and x to another power downstairs, how I can combine them. And the rule was you subtract the exponent in the denominator from that in the numerator. So if I take k minus 1 minus 2k, then I'm left with 2k minus k minus 1, which simplifies to negative k minus 1. So another way of writing this is negative k times x to the power of minus k minus 1. But we already know what negative k is. Negative k is n, so you're left with x to the n minus 1 times n. Now, I don't pretend that you're going to understand that. Most of you will not understand that argument right away. You would have to think about this. You'd have to ponder these letters and why does he keep switching from K to N? It's not an easy argument, but it's a good challenge for you if you want to learn this. To struggle with this, sit down with this for 20 minutes, a half an hour. Try to do it on your own. That's the learning part. Understanding how to fill in the logical steps at each equal sign. Why is the previous line leading to the next line? What rules are you using? How did you deduce it? These are the things we want you to think about. Because here's what's going to happen. If we go to the next page and just look at examples, that's kind of boring, right? Because this is just now you're just doing basic, you know, just being a poor excuse for a robot. But if we look at some of these, let's just take a standard one. We know the derivative of x to the 8th is 8x to the 7th. Well, if we apply it to a negative integer, say x to the negative 8, then by our formula, we're left with negative 8x to the negative 9th. Who has a question? Comment. So sometimes students will say to me, like, why don't you just tell us this? Why do you waste all this time? Why don't you just tell us this is true for any exponent? Well, again, then you're missing part of the fun. Part of the fun is the logical deduction of all this. The pattern recognition. Deriving something in a general setting so that it can be applied over and over again. I mean, that's the fun. To be fair, anyhow, but you guys see, I always feel bad because I expect you guys to like this crap the way I do, and you're probably like, shut up, dude. I promise you I ain't this boring all the time, though. You don't get to see me in real life. Well, some of you may have. Anyhow, does anybody want to ask a question, say anything? You could just make stuff up. By the way, this would be the point in the class when I would scream and yell at you guys, because you guys are going to be terrible at job interviews. Because anytime you're in a job interview and the person interviewing you asks you if you have a question and you sit there and you don't even make something up, they're going to just not think the same of you. You should always ask questions, even if you don't really want to. It makes you sound informed. It makes people think you're paying attention. Even if you're being fake, that's okay too. Oh boy, this Zoom. If we have to Zoom again in the fall, heavens to Betsy's, I'm going to have to get a new career. All right. Cool. So, okay, so we now know how to differentiate certain combinations of polynomials. We know how to differentiate the square root. But really, if you think about it, the types of functions we're capable of differentiating, they don't really, they don't get most things done. So we have to look at more, or I shouldn't say more, but a broader range of functions. What about other functions we can encounter? So So when I say common functions, things like, what is the derivative of e to the x? What is the derivative of sine? Both of these have easy formulas. One is difficult to derive, the other is not. And so what we'll do is we'll derive the simple one, and then you'll just have to trust us that the other one's true. So here's an awesome fact. That we can't prove easily. When I say we, I mean us in Calc 1. But you could definitely get it on the internet or in your book. It's just one we're going to skip. So oftentimes students will say, you know, why do we have to learn about sines and cosines? And why do we care about logs and exponentials? And it's not that we want to do it. No one created these things to make your life miserable. No one said, hey, let's throw sines and cosines in to aggravate students. Let's make them look at log curves and exponential curves in biology class, because that'll really make them mad. That's not how it works. In fact, it's really the opposite. These things, these relationships, the exponential function and the logarithm, the sine function, these things arise naturally in the world we live in. I mean, I don't know how well of instructors you got, or how good your instructors were in trigonometry. Hopefully you actually took it. And I don't know how good of a job they did explaining, you know, why sine is important and its connection with circles and waves. But things like the sine function arise naturally. Anything that oscillates or repeats, anything that goes in cycles can be described by sine waves. So whether you're trying to study water waves, or you're trying to study sound waves, or you're trying to study how heat transfers along a metal rod, there are endless applications or endless things in our physical world that we can describe and try to answer questions. And what pops up over and over again are the trigonometric functions. Now, what about this exponential function? Why is it common in nature? Well, why it shows up is because this is the function that has a very, very, how do you say, natural behavior. So what I need you to imagine is, I need you to imagine the following two scenarios. And maybe you've done this before. And I understand most of you are college students, so maybe the financial piece is different. But I think you guys would probably intuitively get the correct answer here. If I were going to put money in the bank, and someone says, we're going to give you interest on it. So every year you collect more money depending on how much money you have in the bank. And what we have is this thing called compound interest. And essentially what happens is if I put $100 in the bank, but Michael, I'll pick on you because you're at the top, you put $10,000 in. Well, if we both have the same interest, who's going to get more money after 1 year? Well, you put in $1,000 or $10,000, so you're going to earn more interest than I'm going to earn. And if we compound that interest at a regular scheduled pace, whatever, maybe it's every month or quarterly or whatever, what happens is your growth rate, how much money you're earning and growing, is going to be proportional, as you would expect, to how much money's in there. So it goes back to a very, very simple idea. Since you start with more money than I do, you're going to earn more interest than I am. The rate of your account, how it grows, is going to be proportional to how large it is at any given time. Earning 1% of 100 is not the same as 1% of 10,000. Same thing if we're studying bacteria. Suppose I have a petri dish and I have two of them, and I have in one I start with, you know, one cell or whatever, and the other I start with 10,000. What's going to grow quicker? And I think we already know the intuitive answer, the one that starts larger. And so one of the things that we have in nature naturally is that many things, not all things, but many things behave in that manner. Their growth rate is proportional to their size. Now, in terms of math, growth rate is the derivative. It's your rate of change. And so what the exponential function does is this creature has the natural sort of coincidence that its derivative is in fact itself. So the derivative of e to the x is itself. Its growth rate is equal to its size. Now, I don't know if that little blah, blah, blah stuff I just did connected with you at all, but I really hope that you think about it. The derivative of e to the x is itself. That's the only function that has that property except for another function. But the other function that has this property is pretty boring. The only other function that's derivative would be itself would be the function f of x equals 0 everywhere. But that's a boring function. That doesn't have any use. Well, I shouldn't say have any use. It's boring. Does anybody have a question about this? Okay, so what you need to know is the derivative of e to the x is itself. Very cool fact. Okay, what about sine? So we can actually derive this one, so we're going to do it. We're actually going to prove that the derivative of the sine is the cosine, which is a pretty cool fact. So this derivation requires some stuff we did a few classes ago. So the first thing it requires is this limit. The limit as h goes to 0 of the sine of h over h is equal to 1. If you remember, we spent a whole class almost, I think, deriving this. We used the squeeze theorem. We drew circles and triangles. We did some inequalities. It was a pretty complicated limit, but we got to the bottom of it. We were excited. Okay, and then we also, I believe I put it on your homework, a very similar limit is this. We didn't do that one, but I asked you to do it on homework, and you can deduce it from the previous one. And then the last thing we need in order to do this is we also need a fact from trigonometry that most of us probably don't remember. It's called the sum formula or the addition formula for trig functions. So if you have the sine of, say, a plus b, you can break it as sine of A cos B plus cos A sine of B. So we need to recall these three facts, and if we do that and we play the game properly, we can answer this question, or at least do the derivation. Any comments, questions? I don't know why I asked. You guys never do. Okay. Sweet. So let's do it. This will be fun for all 7 of you in attendance. So let's look. What's the definition of the derivative? The definition of the derivative is you take the limit as h goes to 0, and then you plug x plus h in, and then you subtract the function and then divide it by h. So this is the definition of the derivative. So maybe we'll annotate this. Okay, now the first thing I'm going to do is I want to take this limit, and as you know, I want to plug h equals 0, but I can't because I can't divide by 0. So I have to come up with something else. And so what I come up with is I can take the addition formula to kind of get that sign of that ugly thing inside of it, and maybe I can work with that. So if I use the addition formula, this is sine of x times cosine h plus cosine of x times the sine of h, and then it's minus the sine of x still. And so what am I using here? What's my reasoning for this line? This is the addition formula. Does anybody have a question about this? And so what I need to recognize is right now it looks kind of messy, but with those two previous limits that we know, if we recognize that we still have those at our disposal and we rearrange the way everything's written, I can factor this sign out. So I'm going to rewrite this in the following way. I'm going to pull this sign out of these two pieces, so I'm left with a cos evaluated at h minus 1, and then this is all by itself. So all I did is I factored sine of x out of the two terms. All right. So at this point, I need to recognize that I have these two limits, the previous page that I want to use. I want to use these guys. And I also have my limit laws that say I have a sum here. I can break this into two limits. And so that's what I'm going to do. I'm going to use my limit laws. And so I have, on the one hand, I have the limit as h goes to 0 of sine x. And then I have this cosine evaluated at h minus 1 all over h. And then the second piece is, if you look back, I have cos x sine of h over h. Now, all I did there was use one of my limit laws, which say I can take the limit of multiple pieces and break it into each piece. So the next observation is to note that I have two variables. I have h's and I have an x. And the thing to note is that the limits are in terms of h. So x itself is not being affected by h. When h moves, x doesn't change. And so if we use our other limit laws, which we called our constant multiple rules, you can pull those out. So I can write this as sine of x times this limit. And then I can do plus cosine of x times this limit. And these were the two limits that we deduced a few classes ago. This guy right here is equal to 0. This guy right here is equal to 1. And so the conclusion is exactly what we told you would be. You get sine x times 0 plus cosine x times 1, which of course just simplifies the cosine. And that is why the derivative of sine is cosine. Is this an easy argument? No. Could you have done this on your own without someone showing you the sort of the tricks? Probably not. I mean, well, maybe you could. It would take you a while. But at least now you've seen it. And what I would encourage you to do, like I do with all these things, is you should try to get it on your own. So let's make another note, which is super important, is so a similar calculation shows this beautiful formula, that the derivative of cosine is actually negative the sine. And then using the above facts, you can show that the derivative of the tangent is the secant squared. So you now can compute the derivative of the three basic trig functions: sine, cosine, and tangent. And then, of course, if you wanted, using the quotient rule, you can compute the derivatives of the cosecant in the cosine, right? Or excuse me, the secant in the cosine. And we'll ask you to compute those for homework. And we're going to do bunches of examples. Because remember, we can't do any applications unless we know how to compute derivatives. Does anybody have a question or a comment? All right, let's do a couple examples. So suppose we have this derivative. We want to compute 3x to the fifth e to the x. So I look at this and I say to myself, okay, I need to diagnose what's the situation. What kind of function am I trying to differentiate? Is it a polynomial? Well, there's a power piece in there, but it's not a polynomial because I have an exponential function. And so the way I would think about this is I would think about this as, again, you have two functions. You have a first, or an f, and then you have another function, which we'll call g. And so this tells me that the trick here is to use the product rule. So it's the derivative of the first, which I'll switch notations so we're being fair to all the notations, plus leave the first alone and then differentiate the second. And of course, how am I thinking about this? Well, this is, remember, this is f prime times g. Ooh. Oh boy, when the technology goes awry, plus f times g prime. And so to finish this is 15 x to the fourth e to the x plus 3x to the fifth e to the x. And just to clean it up, I'll probably factor some stuff out. I'll factor out 3x to the fourth e to the x, and then I'm left with 5 plus x. Does anybody have a question about this? Any questions, comments? All right, let's do another one then. Let's compute the derivative. For fun, let's switch letters. That's always fun. Let's do the derivative of, we'll use t. And let's differentiate the secant. So to do this, what we'll do is we'll recall that the secant is 1 divided by the cosine. And so by the quotient rule, this is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And so the left-hand side, the derivative of 1 is just 0, so this becomes sine over cosine squared. So what happened to the minus sign? Well, what you might remember is that the derivative of cosine is negative sine. So you're left with negative sine times negative 1, so that gives you positive sine. And then that's over cosine squared. Now, we can write that a little cleaner if we wanted. So if we go to the next page, you have, we'll write it again. So it's sine over cosine squared. But you could write this if you wanted as 1 over cosine times sine over cosine. And that gives you secant t times the tangent of t. So the derivative of secant is secant tangent. Isn't that fun? Any questions, comments, concerns? Here's a cool fact. So let's state this fact. Here's a cool consequence of the product rule. If I have the exponential function not just raised to the variable, but raised to an integer times the variable, this equals n e to the nx for any integer n. So this looks like the power rule, but it's not. So let's make sure you understand that. So, you know, if we were to understand why it's not the power rule, we'll go to the next page because this is important. So the power rule says the derivative of x to the n is nx to the n minus 1. But the exponential rule, if you notice, there's a very big difference here. Here, the base is e, and the variable is x. So, and for the exponential function, the variable is in the exponent. So, for example, if we took, you know, x to the 10th, this would be 10x to the 9th. Whereas over here, if we had e to the 10x, this would be 10e to the 10x. So it's a different rule. And this is a place where a lot of times when we're amateurs, we're just starting, like you guys are, you're going to make mistakes like this. So you got to pay careful attention to this. Okay, does anybody have a question? right, so what you guys should do then is you should pay careful attention to Canvas this afternoon. Hopefully you guys will do some reading on this and work through these examples we did in class on your own, and then I'll post another practice set, and hopefully you guys will work on them, and Thursday we can talk about any questions that you might have. I would also ask you to pay attention to Canvas, so when your grades get, some of your grades will be up sooner than later, just I can't do them all at once. And so if you're really worried about, you want to know what your grade is now, just start sending emails to me every hour until, and then it's like the squeaky wheel gets oiled, and I'll be happy to get back to you and discuss this stuff with you. All right. So if you guys don't have any questions, I say that we call it a day, and I thank you. Does anybody have any questions before we log off? Okay, if you guys don't have any questions, then great. All right, I thank you guys, and I will talk to you on Thursday, if not sooner. Have a good day.